Okay, let's consider the smaller of two regions formed by x squared plus y squared plus z squared equals 64, and the plane x is equal to 3. So all the points where x equals 3, now y and z can be whatever they want on that equation, x equals 3, so that forms a plane, and then find the volume. So just as a picture, imagine you have this sphere of radius 8. You've got an orange, and then you take this plane where x is equal to 3 and you chop. Right? You chop through this. What ends up happening is that chopping here ends up chopping to right at a, let's use a color. So the chop that occurs right here, it's basically cutting off sort of like the polar ice cap or something of an orange, yeah? And so this smaller piece over here is what we'd like to find the volume of. And here's the thing, in that smaller piece, given a fixed y and z, we can say that x goes from, so in the smaller piece over here that's shaded over on this side, x goes from the smaller x value of 3 to the larger x value of root 64 minus y squared minus z squared. So why is this the larger value? Well, imagine that y and z are both 0. So then, the point that's far over here, that x coordinate should be 8. Okay, so this tells us, because it was easy to talk about what x goes from and to, given a y and a z, we should set up. It's going to be most convenient in this problem to set up a dx, then d something, then d something. But the point is the innermost integration should be with respect to x. Then if you project onto the yz plane, so we should look where, if we plug in 3 up here, yeah? So we're trying to see, so that this circle right here, that's what the projection is going to look like, just onto the yz plane. So that's going to be looking at x squared plus y squared plus z squared equals 64. Where does that meet x equals 3? And you can find that by plugging in 3 for x. So 3 squared plus y squared plus z squared is equal to 64. So y squared plus z squared is equal to 61. Yeah, so we're on, oh my goodness, need to subtract 9. So 64 minus 9, in other words, y squared plus z squared is equal to 55. So what we end up projecting onto on the yz plane, so let's say there's y there and z there, is you end up getting a filled in circle of radius root 55. Okay, and then I'd say use polar. So let's just go ahead and set this up, yeah? So let's say we set this up as a dx on the inside, then dy, then dz of, here the function 1, because we're finding the volume, but the 1 could be replaced with some other, just f of x comma y comma z if we were given some general function. So x going from, let's give a little more space here, from 3 to root 64 minus y squared minus z squared. Then the y, let's just take this and solve for y. Yeah, so y is equal to plus or minus root 55 minus z squared. So the y goes from negative root 55 minus z squared to positive root 55 minus z squared. And then when you project onto the z-axis, yeah, I guess we'll just do this. We'll put y here, we'll put z here. Then when you project onto the z-axis here, you go from negative root 55 to positive root 55. Okay, so there we're done. Well, let's just say that we're done with the problem, but if you were to actually now to evaluate, we'll just kind of outline this. To evaluate this integral, what I think would make most sense to do is evaluate the inner integral, evaluate the innermost integral, right? So the inner integral here would be just this part right there. Then, for the dy dz integral, I would switch to I don't know what you say, like polar, but in the but not in the xy plane. Then switch to. You have to kind of create your own homegrown polar coordinates, polar in the yz plane. That I think would make the most sense to make this the easiest to do. Okay, let's just comment that I think a good problem to try on your own, or to at least set up in in integral for, is integrate. We keep using the function 1, so let's just say, how about you had the function f of x comma y comma z, it doesn't really matter, but let's just pick an easy function to integrate x, y, z over the tetrahedron bounded by the planes x equals 0 and y equals 0 and z equals 0 and the plane 2x plus 2y plus 3z is equal to 12. So I would say this can be challenging at first, but it'd be really good exercise. There are 6 possible ways to set up the integral, and so please try all 6. If you really want to get a good sense of what's going on here, challenge yourself. Please try to set up all 6 triple integrals. Properly set up, all of the 6 triple integrals should, if you were to go through the evaluation process, you should end up with the same final number in all cases.